Here's a problem from chapter 11 where we've got a bug on a platter. So this is top view. Here's the bug. And the bug goes to the center. Okay, so walks along the surface of this platter. And initially the platter was rotating at, say, 10 radians a second. And the question is, what's the final rotation rate, the angular speed? And so we can treat this as a system, the bug and the platter, where we can say the sum of the external torques is equal to 0 because nothing is slowing the system down. Now the bug is certainly exerting an internal torque, but we don't know anything about that. And so we can use the sum of the external torques is equal to 0 to say that the angular momentum initial must be equal to the angular momentum final. And in this case, the angular momentum direction hasn't changed. So the direction of angular momentum is the same direction as the direction of omega. So you can use your curling right-hand rule and see that it's out of the screen. So our job is to really figure out what's the new angular speed, right? Angular velocity. Speed, we know. The direction we already know is out of the screen for the velocity direction. So now we just need the magnitude. So the initial situation is just the moment of inertia of the disk plus moment of inertia of the bug, treating it as a point particle, right, that sits out some distance away, times the initial angular momentum is equal to the moment of inertia of the disk plus the new moment of inertia of the bug. Now notice, moment of inertia of the bug, because it's all the masses sort of right together where it sits, is for a particle mr squared. So if this is the r in the initial case, that's the moment of inertia of the bug. But at the end, in the final case, the r of the bug heads towards 0 in the final situation. So this becomes a 0 times omega final. And that's why our values are different, the initial to the final value. And we're expecting that to be a bigger value. It's like the skater who brings his or her arms in as they're doing a spinning move. So it just is a matter of finding the moment of inertia now. So moment of inertia of a disk, we look in our table and we find that's 1/2 mass of the disk times r squared. And then the moment of inertia of the bug initially is just the mass of the bug times its radius. It's on the edge squared. So this one becomes 1/2, looking at the values, 0.1 kilograms times 0.1 meters squared. And this one is 0.02 kilograms times 0.1 meters squared. So this becomes 0.002 kilogram meters squared. And this becomes 0.005 kilogram meters squared. So that's really all the information we need. We can just plug everything in. So I've got, plugging this value in here, I've got 0.005 kilogram meters squared plus 0.002 kilograms meters squared times my initial omega, which was 10 radians per second, must be equal to, in the end, 0.005 kilogram meters squared times my final omega. So final omega is just equal to, this becomes 0.007 divided by 0.005, or 7/5. And so this gives me a final angular speed of radians per second. Okay, so that's part A. Check. All right, this is a bunch of parts. Now part B, what's the change in kinetic energy? So then for part B, we need to find the kinetic energy to start with and then the kinetic energy final. So the kinetic energy to start with is going to be 1/2 I of the disk plus I of the bug omega initial squared, so that's just 1/2 times 0.007 kilogram meters squared times 10 radians per second squared. So this becomes 0.35 kilograms meters squared over second squared, which is, of course, a joule. For the final situation, this becomes 1/2 the I of the disk, which is just the 0.05 kilogram meters squared, and 0 for the bug, times omega final, which would be 14 radians per second squared. And when I work that out, my final kinetic energy becomes 0.049 kilogram meter squared per second squared. Remember, again, the radians drop out as we need to, and that's joules. So we've actually increased the kinetic energy. The change in kinetic energy final minus kinetic energy initial, is going to be 0.49 minus 0.35, 0.14 joules. Okay, where did that energy come from? Well, that came from the work done by the bug as it crawled, because it had to, specifically the frictional force between the bug's feet and the platter, that applied some torque to the platter itself. We don't have to know about it, but that's there. So we could have actually calculated. We know the work done by the friction, by the bug, if you like, its internal energy to create that friction, but, well, to keep the feet moving at least. And so that gives us our 0.14 joules. Now, the rest of the problem says if the bug crawls back to the outer edge, what's the angular velocity? So for part C, we're going back to the same situation. So if there's no friction in the situation, then we must go back to, omega goes back to 10 radians per second. I don't have to calculate anything. The bug goes back to the original situation. What's the new kinetic energy? So the kinetic energy would then be the same in this new situation. So that would be your 0. Kinetic energy would be 0.35 joules. And this time we would have a loss of kinetic energy, and that would be due to the work done by the bug. Again, this is negative work. You can think about when you lift something up and raise it back down, the weight does first, the Earth's gravitational field does first negative work and then positive work. So altogether, it's done net work of 0 as far as that goes.